Thanks for joining. We're about to do some practice problems, which is one of the best ways that we have to help us learn. Now, if you haven't tried these problems yourself, please try them yourself first. There's this beautiful button. It's somewhere along here called pause. Make use of it. See the problem? Pause. Try it yourself. Then if you need to, you can unpause, and we can compare answers. In this way, you get engaged, you'll learn, you'll succeed. And that's what we want, your success. Let's get going. Number 1. Find an implicit solution for a very long thing which contains the point xy equals 1, 1. Now, note we do have a derivative, so it's not surprising. We are in, of course, differential equation, so you would expect a derivative somewhere. And we look at this and like, oh, this looks terrible. This looks hopeless. And we'd say, yes! Because when something looks hopeless, we have a way. So, in particular, we strongly suspect this is exact. There's another clue that this is exact. So, exact tends to be tied to implicit solutions. And oftentimes, if they specify implicit solutions, that's also another hint. So, what do we need to do? Well, the first thing I want to do before I get too far along is to say, this y prime here, let's think of this as dy over dx. And then I'm going to multiply through by dx. So if we do that, we'll rewrite. We have 2y arctangent of x over y squared plus 1 plus 4e to the minus 2y plus 3x squared dy plus log y squared plus 1 over x squared plus 1 plus 6xy minus 12 cosine 3x, all of that now with parentheses times dx equals 0, right? Because we could have always added some parentheses around this other part. The reason I want to do that is because writing in this form really drives home what our technique is going to be. Namely, we have two pieces, one part attached to dy, one part attached to dx. And we're after a particular function. And what does that mean? Well, we're after a function such that if we took the derivative with respect to y, we'd see something that looks like this. And if we took the derivative with respect to x, we'd see something that looks like that. So we say, oh, okay, well, that's what we're after. So how do we get there? Well, the great thing is we understand. So the thing with the dy, we're just going to integrate that with respect to y. So it's almost like we're just taking this piece, and we're just going to throw it in front of an integral, or maybe I should say throw an integral in front of it. So we have 2y arctangent of x divided by y squared plus 1 plus 4e to the minus 2y plus 3x squared. All right, now we integrate. Pay attention. Notice we're integrating with respect to y. So what does that tell us? Well, it means that y is the variable part in this integral. Anything with an x is a constant. So for example, this arctangent of x, well, that's normally a very beautiful and exotic function. But for the purposes of this integral, it's a constant. So you can say, okay, so this is arctangent of x, just the constant comes out of this piece. What's the integral of 2y over y squared plus 1? Well, it's one that hopefully you recognize. And you say, oh, y squared plus 1 downstairs, 2y upstairs. Well, 2y is the derivative of y squared plus 1. So this is u and the du. So that becomes log of y squared plus 1. All right, so that's the first piece. Integral of 4e to the minus 2y. All right, we got to get really good at exponentials, right? So we're integrating e to some constant y. We'll bring the constant and divide by it. So we're going to still have an e to the minus 2y, but now take the 4 divided by minus 2, gives us minus 2 e to the minus 2y. And the integral of 3x squared, Well, 3x squared is all constant, right? Because we're integrating with respect to y. So we'll have that constant times y plus, and here's where the magic happens, something which doesn't depend on y. So some function of x, some unknown function of x. That's where it's all going to come together. Okay, now that we've done that, the function we're after has this form, but we don't have that nailed down. So here's where we come here to this part. We're going to repeat the same thing we just did. So namely, this thing with the dx attached, we're going to integrate. So we integrate. We have our log y squared plus 1 over x squared plus 1 plus 6xy minus 12 cosine 3x dx. And so now we're integrating, this time with respect to x. So treat anything with a y in it like a constant. Well, okay. So for example, in our first term, we have a log of y squared plus 1. Well, that's a constant. All right, that just comes out. And then we say, well, what's really going on with respect to x? It looks like an x squared plus 1 downstairs and just 1 upstairs. 1 over x squared plus 1. Do we know that integral? Of course we do. Of course we do. It's arctangent of x. Perfect, perfect. Integral of 6xy with respect to x. So the y is a constant. Integral of x is a half x squared. And times that by the 6. Half times 6 makes 3x squared y. All right, now we come here. Integral of cosine is positive sign, right? So there's a minus. So we're still going to have a minus, but be careful. Keep track of your plus minuses when you're dealing with sines and cosines. We also need to account for that 3. And we do that similar to what we did up here. We divide by -2 up here. Here we divide by 3. So that gives us minus 4, 12 over 3, sine of 3x. And plus something which doesn't depend on x, so it's some function of y. All right, so good news is we've done most of the work. Now we're going to try to merge these together. And this problem doesn't ask us to say how do we know it's exact, but here's how we know. We look at this and say, all right, pieces which involve both x and y need to match. So you'll see there's 3 pieces up here, there's 3 pieces down here. So I'm thinking of a piece, something separated by plus or minus. And we say, well, hey, this part, arctangent of x log of y squared plus 1, matches with arctangent of x log y squared plus 1. So those match. And the 3x squared y matches with 3x squared y, and those match. So the pieces that involve both x and y agree. So that means it's exact. Woohoo! Yay us! Yay us! Now, those pieces will be part of our final answer. And anything which only depended on y from the integral came in with respect to y will be part of our final answer. And in a similar way, anything which depends only on x, which came out of our integral with respect to x, will also be part of our final answer. So putting it together, we have the following. We have this part. So we have arctangent of x log y squared plus 1. We'll go ahead and put the 3x squared y right next to it. The minus 2, e to the minus 2y, and the minus 4 sine of 3x, and that equals to some other constant. And that's the general form. So again, we have the 2 pieces where they involve both. They overlapped. We checked that they agree, so we were like, yes, definitely this is working. The part which only involves y, and the part which only involves x. So that's how we assembled our left-hand side. Now, we're not out of the woods yet. There's still one more thing to do. Namely, we have this condition. It has the point. xy equals 1, 1. So that gives us what the right choice for b is. So how do we do it? Well, we're going to plug in x equals 1 and y equals 1. So if we do that, we get arctangent of 1 log of 1 squared plus 1 plus 3 times 1 times 1 minus 2e to the minus 2 times 1 minus 4 sine of 3 times 1. And that equals b. So there's our constant. Now we can maybe simplify a few pieces. What can we do? Well, this is arctangent of 1 is pi over 4. And 1 squared plus 1 is 2, so log of 2. Here we have a plus 3 minus 2e to the minus 2 minus 4 sine of 3. Now you look at this and say, that's our constant? Yeah, that's okay. Constants don't always have to look nice. And we don't have to put a lot of thought into it. It just comes out. So, to finish it up, we just need to replace our b with our new value and rewrite our answer all together. So, our final answer. Lots of writing on this problem, but that's all right. The process makes sense, and that's the key thing. We want to have things make sense. So arctangent x log y squared plus 1 plus 3x squared y minus 2e to the minus 2y minus 4 sine of 3x equals pi over 4 log 2 plus 3 minus 2e to the minus 2 minus 4 sine of 3. And there we go. There we go. An exact problem and a wonderful process. All right, great start. Yes, let's keep going. Woohoo! Number 2, solve 5x y to the 4th y prime equals negative 4x squared plus x y to the 5th. And we have a condition y of 1 equals 1. So it's an initial value problem. Well, what kind of problem do we have? That's always a great question. It's not looking promising for exact because it doesn't look completely hopeless, and but it doesn't look separable either, and it's not looking good for linear first order as it currently is because there's y prime, but there's a couple of places where y shows up. But notice how everything has y to a power. Now this is suggestive that maybe we can rewrite it into something which is a little bit more convenient. So let's think of what we can do. Now, in particular, let's make this y to the 4th in front of the y prime go away. So I'm going to start by dividing everything by y to the 4th and see what we have. And so, all right, because I'm liking y prime by itself as much as possible. So here we have 5x times y prime equals minus 4x squared over y to the 4th plus x y. Okay, interesting. Now, if we move this across, this would become 5x y prime minus x times y equals minus 4x squared, and I can write it as y to the negative 4. And here's the thing. If we took our thumb and covered up that y to the negative 4, what would we have? We'd say, well, it looks linear first order. It's like, but what about that y to the negative 4? Keep your thumb down. No, we can't do that. But if you can do this, this is a very particular type of differential equation. What do we have? Bernoulli. So this is Bernoulli. So we say, we're looking at this, and we say, we're going to use Bernoulli. Now, what does that mean? Well, so Bernoulli was the name of a family of mathematicians and physicists, and their idea was, for this kind of differential equation, make a substitution y to a power. So u equals y to some power. Now, how do we figure that out? Well, here's what we're going to do. Do you see this y to the fourth. Or rather, this y to the minus 4. Once you have it in the form where you can like, oh, if I cover up this, then it's like, oh, it's linear first order. You're going to want to make this go to the other side. Okay, so we're going to multiply both sides by y to the fourth. You're probably thinking like, Steve, what did you do? That's where you were starting from. And I get where you're coming from. It's like you divided by y to the fourth, and now you're multiplying by y to the fourth. Well, it's because I just wanted to understand what the problem was and what the procedure was. So it's not that we did something and gained nothing. We did something and gained insight in how to proceed. So we currently have it as 5x y to the fourth y prime minus x y to the fifth is equal to minus 4x squared. Now, on another side note, if you can spot the substitution earlier, go ahead and do it. But if you can't, work through the process. Now, how do you figure it out once you've done this? Once you've recognized that this is Bernoulli, and you've moved the y over across, so there's no more y left, the part that's not attached to the y, that's the substitution we're going to be making. So we're going to let u be y to the fifth. And what do we have? Well, take the derivative. Chain rule, 5y to the fourth times the derivative of y, y prime. And then we're like, oh, promising. Because we see something. See, we have a 5y to the fourth y prime. Perfect. Almost as if the person who wrote this problem planned it that way. I suspect they did. So let's see what we have. 5y to the fourth y prime is our u prime. We still have an x, so it's x u prime minus x and times u is equal to minus 4x squared. Now, quick check. Did we account for all the y's? Yes. So this is a good substitution. And now we say, okay, now we're back into our linear first order, because we don't have to like cover that piece up. So we're back into a more straightforward one. So what happens next? Well, we say, okay, from here, we want to make what's in front of the u prime be a 1. It's currently an x. So we're going to multiply everything by 1 over x. U prime minus u is equal to, and over here, minus 4x. All right. Now, from here, what comes next? Well, the next thing we need to do is we need to do our integrating factor. So we've got our 1. So there's a 1 here. That makes us happy. We like that there's a 1 in front of the u prime. So we say, all right, you come to what's in front of the u. In that case, it's this minus sign, which really is just another way of saying minus 1. So our integrating factor is e integral minus 1 dx. Well, the integral of minus 1 is minus x, so it's e to the minus x. So we're going to multiply both sides by e to the minus x. And with all of that work, we have u prime times e to the minus x minus e to the minus xu is equal to minus 4x e to the minus x. So, good news. The left-hand side, the parts with the u and the u prime, by design, this will be easy to integrate because it's a derivative. It's the derivative of our integrating factor times u. And you can just check, right? Take the first times the derivative of the second, e to the minus x u prime. Then take the derivative of the first is minus e to the minus x times the second u. All right. Well, so now we've reduced our problem to saying the only thing we have to do here is integrate the right-hand side. Okay, so, well, let's do it. Let's do it. Yeah. Woo. Integrating both sides. And what do we get? Well, we're going to get e to the minus x times u is equal to, and over here, well, we'll need to do a little bit of work. So how do you integrate something like x e to the minus x? You use integration by parts. And so that's all right. We know that, right? So integral minus 4x e to the minus x. We'll differentiate this part. We'll call that our u. E to the minus x as our dv. So du is minus 4 dx. And v is minus e to the minus x. So we get our u times v. Minus 4x minus e to the minus x. So there's our uv. Minus the integral of v du. Oh my goodness, so many minus signs here. That's all right. That's why we're going to make sure to use our parentheses. Minus, minus, that makes a plus there. Minus, minus, that makes a plus there. So we end up with 4x e to the minus x. And here, when we integrate again, we'll get another minus coming down. So we'll end up with another plus 4 e to the minus x and plus some constant c. So that's what's over there. So 4x e to the minus x plus 4 e to the minus x plus c. And we're almost out of the woods. Well, what can we do next? The next thing we can do is we can multiply through by e to the x. That will give us that u is 4x plus 4 plus some constant c e to the x. But remember, what's u? We have to substitute back. So u is y to the fifth. So y to the fifth is equal to 4x plus 4 plus c e to the x. All right, well, we need to plug in now. So what do we plug in? We have y of 1 equals 1. So we have that 1 is equal to 4 plus 4 plus c times e. Or you can subtract there, and we get that subtracting 8, c is equal to 1 over e times a negative 7. So minus 1 over e times 7. And, or if you like, that's minus 7 e to the minus 1. All right, we're almost there. Put that in, and we get y to the fifth is equal to 4x plus 4 minus 7. And then we have e to the minus 1 times e to the x. And you can put those together upstairs as e to the x minus 1. And the last thing, if we want to solve for y, get rid of that fifth power. What do? You take the fifth root. So y is 4x plus 4 minus 7e to the x minus 1 to the 1/5 power. Nice, nice, nice. Now, you probably think, Mike, how many times are we going to do integration by parts? We did that last quiz too. It's a good technique. It's a beautiful technique, and it's a good thing to know. So be ready. You never know when you might encounter it out in the wild. But that's the process, a beautiful thing. And really, the big thing is just figuring out, how do you recognize it? Don't underestimate the importance of learning to recognize things. That's why we do problems. The more that we do, the easier it becomes to recognize what types of problems we have. So keep it up. Keep studying, and it's going to become second nature. All right, good. Let's keep moving forward. Number 3, find the general solution. So good, no initial conditions. For y double prime is equal to 3 times y prime squared. All right, now, before we get going too far, couple of comments. Notice there's a y double prime. And at this stage, we haven't done a lot of things with y double prime. So that's going to sort of dictate what we're doing. But there's two things I want to talk about here. Namely, when we have the general solution, because we have a second derivative, it's a second order differential equation, there should be two different constants. In general, if you have an nth order differential equation, n constants in the general form. So, all right, so we know we're going to have a couple of different constants show up in our final answer. The other comment, besides being a second order, what else do we see, or in this case, not see? That is to say, there's something missing here. There's no x terms. So we say, oh, that means that we can use this sort of substitution that gets us in the setting of order reduction. And this one is a little bit unusual the first 2 or 3 times that you do it. So it's good that we're practicing. So the idea is pretty straightforward. We're going to make a substitution. The y is going to stay as y. No big deal. Y prime, we're going to replace that by u, where, to be clear, u of y is y prime. So we're thinking that if you plug y into the function u, out comes y prime. So now comes the what? Y double prime is going to become u prime u. And this is the part that makes you go, no, that doesn't seem right. Bah! But here's the thing. Let's unravel this a little bit further. When you actually look at what we're trying to solve for, we're really trying to solve for things as functions of x. So u y of x is equal to y prime of x. So, given that that's true, when I'm coming to y double prime, we're taking the derivative with respect to x. So y prime derivative of that would be double prime. Now, take this derivative. Well, you'd have, by the chain rule, derivative of the outside, leave the inside alone, times the derivative of the inside, which is y prime of x. Or, if we simplify, we say, well, look, we just call this part u prime, and y prime is u. So that's how we get that y double prime is u prime u. So this is the sort of the rule that we're going to follow when we make our first layer here. And when we do order reduction, what we're going to do, this sort of our game plan, just so we know what's coming. We have a second order differential equation. So instead of trying to do it all in one big jump, we're going to sort of make it a two-step process. So we're going to get to a first order differential equation and get to another first order differential equation. So we're going to work our way up the ladder, as it were. So with all of this, we go through and do our updates. So we have y u prime u is equal to 3 u squared. Okay, so I'm just following this. Y stays as it is, u prime u, u squared. And notice we just have y's and u's, and it's first order. And it's actually pretty straightforward. As first orders go, this is a separable differential equation. So, all right, we clean it up. So we have the u goes there, that cancels. And so we say, what do we have? Well, we have the following. The u prime, we're thinking that as du dy, right? Because u is a function of y, times y is equal to 3u. Or, rearranging, du over u is equal to 3 over y dy. All right, good. Now we integrate. And what's the integral of d over u? Log of u. Integral of 3 over y? Well, 3 comes out. Log y plus c. All right. And we want to get u by itself. So we're going to take both sides and take e to that. So e to the log of u is going to become u. Here, we'll do this carefully. This is going to be e3 log y times e to the c. And we can move that 3 in front, this 3 in front of the log. We can move it upstairs. So that's log of y cubed. And e to the c is just another constant, so we'll just rewrite it as c. So we really have some constant y cubed. Okay, so there we go. Are we done? No. What was u? U was y prime. So we say, oh, all right, well, y prime equals c y cubed. And so we've done one layer. And now we need to do a second layer. All right, great. So just recapping, from this differential equation, we were able to get to here. Phew. Now, for the next step, what do we do? Well, now we're ready to solve this. And this is also a separable differential equation, but now we're thinking y is a function of x, dy over dx is equal to some constant c y cubed. So we separate. We say, all right, dy over y cubed is equal to some constant c dx. Or y to the negative 3 dy is some constant c dx. Now we integrate both sides because we've done our separate. Next comes our integrate. And what do we get? Well, you add 1 to the exponent, divide by the exponent. So you add 1 and you get negative 2. Divide by negative 2, negative 1/2. Y to the negative 2. All right, that's the integral of y to the negative 3 equals, over here, c x plus another constant. Well, now we can multiply through by negative 1/2. So we get y to the negative 2 is equal to, well, I shouldn't say negative 1/2, multiply everything by negative 2. But when I multiply by negative 2, negative 2 times c becomes c. It just gets absorbed. And negative 2 times d, it can become d. It gets absorbed. And finally, we're ready to say, if I want just y, now I can say, what is it? It's cx plus d to the minus 1/2 power. And there's our nice general solution. We did it. We did it. Yay! Yay us. Yay us. All right. Good. Good. Well, there you go. This is a fun one. I hope you enjoy it. I hope you enjoy all of these. Let's keep the joy coming along. Next problem. Oh, yeah. Number 4. Find an implicit solution to y prime equals 2x y to the 4th over 3x squared y cubed minus x to the 4th. Whew. Okay. By using the substitution, y cubed equals x squared u. All right, so we're doing a substitution. It's a little different, a little bit of off from what we normally do. But they're just telling us, this is what we want you to do. So let's see if we can figure this out. Well, of course we can, right? Our powers combined. I believe in us. Now notice here, the part that has the derivative is the y. Why do I bring that up? Well, that tells us the substitution. We're going to replace our y's. Now, we have some sense of how to replace our y cubes, but we also need to understand how to replace the y primes. So, to get to that, what do we need? Well, I tend to try to get, the y semi-isolated. I'm not going to get it completely. Y cubed is pretty good. And let's take the derivative here. So if we take the derivative, we'd have 3y squared y prime. And when I say take the derivative, I'm talking about take the derivative with respect to our variable x equals, product rule, 2x times u plus x squared u prime. All right. Well, so the easiest thing for us to do was if we could put something that looks like a 3y squared. Oftentimes it'll already be there. This time it's not, but we can fix that. So we're going to take our original equation and multiply both sides by 3y squared. So doing that, what will we have? We will get 3y squared times y prime is equal to 2x y to the fourth times 3y squared over 3x squared y cubed minus x to the fourth. Now, notice we can clean this up a little bit. 2x times 3 is 6x, and y to the fourth times y squared is y to the 6th, which is y cubed squared. Why point that out? Well, because we're trying to replace the y's, and the easiest thing to replace is a y cubed. Downstairs, we have a 3x squared times a y cubed minus x to the fourth. So now we have plans. We say we're in great shape. We know how to replace this 3y squared y prime. And we also know how to replace our y cubed. So we know how to do these pieces. So we can account for all of the y's. When you're doing a substitution, you've got to account for everything. So carrying that substitution out, we have 2xu plus x squared u prime. All right, that's our 3y squared y prime is equal to 6x times x squared u squared, that's from here, divide by 3x squared times x squared u minus x to the fourth. And you might be like, oh, this is looking terrible. This is not looking promising, Steve. Well, hold on. I suspect something nice is about to happen. Let's see. We have 6x times x to the fourth u squared divide by, here we'll have 3u times x to the fourth and minus x to the fourth. Do you notice anything about these terms? Do they have anything in common? Yes, they do. There's x to the fourth is common to everything, which means we can get cancellation. So the way that would work is you'd multiply top and bottom by 1 over x to the fourth. And if you do that, you get 6x u squared over 3u minus 1. All right, that's pretty straightforward. We can work with that. Life is good, right? Yes, life is wonderful. It's wonderful. All right, well, now what? Well, our goal is let's try to get u prime by itself. So let's subtract. Okay, so we now have x squared u prime is equal to 6x u squared divided by 3u minus 1, subtract 2xu. Well, what would we do? Well, we'd want to get a common denominator, and so we'll multiply this by 3u minus 1 over 3u minus 1. So that would give us 6xu squared. And everything's going to have that 3u minus 1 denominator. And here we have this 2xu times 3u. Don't forget the minus. So that would be minus 6xu squared. And here we have a minus plus 2xu. Well, nice! Cancellation! And so we really have 2x, and I'm going to write this as u over 3u minus 1. Okay, all right. We're in good shape now, right? Because this all equals, we'll go ahead and write it over here, x squared and u prime du over dx. We can separate. So we're going to do that now. And so we're going to move the dx and the x squared will come over to the x side. This u over 3u minus 1 will come over to the u side. And if we carry all of that out, what will we have at that point? Well, let's see. Let's be careful here. So we'll start with the u's. So this is going to, when we come over, it flips. So we get 3u minus 1 over u du equals, and over on the x side, well, we have a 2x. We're dividing by x squared. So that will give us a 2 over x. And then we have a dx. Okay. Good. 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 Oh, this is feeling really good. And what can we do? Well, now we can integrate. Okay, so we're going to integrate both sides. Now, the 2 over x, hopefully by now we're like, we know how to integrate 2 over x. We see that all the time. We're really good at that. But what about here? Well, notice this integral, you can split it up because this is a good minus. See, over here, this is a bad minus because it's a minus in the denominator. But when you moved it over, it became a good minus because it's in the numerator. So you can split it up and say, well, this is really 3 minus 1 over u du. We say, well, that makes it pretty straightforward. So we get 3u minus log of u. And on the other side, we get 2 log of x and plus c. Well, we're basically done, except for one thing. We got to substitute back in. So we'll do that in just a moment here. But first, I want to get rid of the logs. So I'm going to take both sides to the e power. And if we do that, well, what will we have? We'll have e to the 3u. And this becomes times e to the minus log u, or e to the log u minus 1. So that's a 1 over u. Here we'll have e to the 2 log x. That 2 goes upstairs. And in some sense, that's really what we did here. Log of x squared, so we get just x squared. And then the e to the c becomes a constant c. Or we could say, hey, this is e to the 3u is equal to some constant x squared times u. All right, we're almost done. We're just at the last step. Why is this not the answer? We made a substitution, and so we have to go back. So we come back here. We say, okay, our substitution, we have that y cubed is equal to x squared u. And we look at this and say, well, that's an x squared u. Okay, well, that's cool. And so we could say this becomes some constant c y cubed equals e to the 3. Now what about u? Well, u is equal to y cubed over x squared. So 3 times y cubed over x squared. And I should pause and say, you could have come back here and made that substitution for u and be done. But I just want to show you, you can still always do a little bit of cleaning up. And it's good to get into the habit of seeing how to clean things up. If we take both sides and take it to the 1/3 power, what would happen? So this will be the final little thing to do. Over here, well, constant to a 1/3 is a constant. Y cubed to the 1/3 is y. So constant times y is equal to, and here, because we have that 3 times a third is 1. So it's e to the y cubed over x squared. And that's about as clean as you can hope for, because it's pretty clean. So there you go. So this looks pretty hopeless, but really at the end, say, oh, it turned out to be not so bad. Now, we wouldn't be able to get y by itself. We could get x by itself, but we don't need to. Our goal was just to find an implicit solution. So we didn't have to solve for y or for x. So again, you could have come back here and put in your substitution for u, full points. The rest of this was just saying, oh, look, here's some ways to rewrite things. And that's a pretty good skill set to have. Spoilers, that's algebra. Don't we love algebra? I think we should. I think algebra is great. Number 5. A population of fish measured in tons had a stable population of 150 tons. A disease reduced it to 50 tons, at which point the population started recovering, growing at the rate of 5 tons per year. Assuming the population follows the logistic model, what will be the population after 10 years? All right, cool. So there's a key word here, logistic model. I guess it's the key phrase. What does that say? Well, it tells you what the assumption is about how growth behaves. In particular, the underlying assumption is that the change in population, or in other words, the derivative p prime, behaves like some k times p times m minus p. Now, k, the larger k is the faster population grows, so that's good to understand. But one of the key things about the logistic model that's going to show up in a few problems, and it definitely shows up here, is what is m? Okay, so if we can understand m, this is going to help us a lot in this problem. So there's a few ways to think about m. One way to think about it is if you think of p equals m, that's actually a solution to this differential equation. It's what we call a constant solution. Because if you plug it in, p equals m, you get 0 over here, and then the derivative of a constant is 0. 0 equals 0. But in particular, what really happens is for the logistic model, I'm going to draw a very small picture here, we have this value m. If you're below m, you start moving up towards m. And if you're above m, you start moving down towards m. This assumes that k is positive, which for this problem makes sense. So what's the punchline? So m, you can think of as a couple things. It's the carrying capacity. That's a phrase I heard, and I like the idea. It's sort of how much does the environment can it sustain. It's also the long-term behavior. Now, you'll notice when it started here, it says it had a stable population of 150 tons. What does it mean to say that the population was stable? if you say something is stable, what's true? Well, what's true is it's found a nice point. It doesn't need to grow. It doesn't need to shrink. That's where we're at. So what is this 150? The answer is the 150 is m. So m equals 150. So that's the first idea. So they were telling us that m is 150, but didn't use the phrase m equals 150. We had to figure that out from context. Okay, good. Now, let's think about what else we have here. So the population had a bit of a wipeout from a disease, short term, I hope, got down to 50 tons, and then it started growing again, recovering. So what are these numbers? 50 tons and 5 tons per year. Well, what those are giving us is that's giving us some sort of initial conditions about where we're at. So we have that P of 0 is 50, and P prime of 0 is 5. So how can we use that? Well, we know that P prime is equal to K P 150 minus P, because we figured out what M is. What we can do is we can plug these values in. And so we say, nice, let's do that. Okay, so plugging in, what do we get? So at time 0, we get that 5 is equal to K times 50 times 150 minus 50. Well, that's really 100 times 50 is 5,000. All right, very nice round number, but that's all right. That's when we're doing problems by hand, right? We like nice round numbers. Or we get that K is 1 over 1,000. Okay, so we figured out M from context, and we used this initial information to say, we have that P prime is equal to 1 over 1,000 times P 150 minus P. And we also, by the way, know that our initial population is equal to 50. Okay, now, what do we want? Well, all of that is to help us get to our real question, which is what's going to happen after 10 years? So our goal is, given this differential equation, this initial condition, we want to find P of 10. Now, you might say, this is going to be hard. And you're like, wait a second. We have a formula. There's something on the formula sheet. And so in particular, what do we have? The formula sheet says P prime equals K P M minus P. That tells us that our population is equal to, you take M P0, divide by P0, plus M subtract P0 in parentheses, e to the minus KMT. We know M, P0, and K. So we say plug those in. All right, what do we have? We have M is 150, P0 is 50, and then P0 is 50. M minus P0 is 100. E, and now to the minus K over M. Well, K is 1 over 1,000, and M is 150. And, okay, so it's minus 1 over 1,000 times 150 times T. All right. Well, we can definitely clean some things up to make life simpler. So, for instance, we can divide everything by 50. So that will become a 1. This will become a 2. And we can now say what? Well, what's P of 10? So P of 10 is equal to, we have the 150 upstairs over 1 plus 2 e to the minus 1 over 1,000 times 150 times 10. All right, well, okay, you can get one of the 10s to knock off. So, 10 over 1,000, 1 over 100. You can get another 10 to knock off. And 15 over 10, and we'll not divide by 5. We get 150 over 1 plus 2 e to the minus 3/2. And without a calculator, that's the best we can do. And that's all right. That's what we're trying for. So what's going on here? What is this question asking us? It's really trying to make sure to ask the question, do you understand the logistic model? Do you understand what the pieces are? Can you extract the information you need from the word problems and use that to figure out, oh, here's the actual solution. I have the individual pieces, and I plug it in, and I get what I need. Yes, we can do that. We can do that. Cool. Number 6. In a zombie apocalypse, the number, P of T of zombies, measured in the thousands, follows a logistic model. When P equals 6, or to say that there's 6,000 zombies, the rate of growth of the zombie population was measured at P prime equals 2. Similarly, when P equals 12, or there's 12,000 zombies, it was P prime equals 3. Determine the long term, i.e., what happens as T goes to infinity for the zombie population. All right, so what are we going to need to do? We're going to need to use our brains. Use our brains, right? Yes, exactly. All right, but okay, what's the key? Well, logistic model. There we go. So this ties back to the logistic model. Nice. That gives us a lot of information. And so we say, okay, we know we have our P prime is equal to K P times M minus P. So that's the logistic model. So we know what setting we're in. What are we looking for? Well, the question says, determine the long term. In other words, how many zombies are we going to end up with? So as we let time head off to infinity, what do we get? So, do we understand the logistic model? Well, the logistic model says what? You have this value m, and you're going to go up towards m if you're below it, or down towards m if you're above it. So, this m, this is the long-term behavior. So, that is to say, hey, our problem is find m. So that's what we're after. Once we find m, then we know what's happening. So how do we do it? Okay, well, for that, what can we do? Well, let's see what we have. We have some pieces of information. So in particular, we have two nice pieces of information. When P equals 6, P prime was equal to 2. So what we can do is we say, oh, let's use that information to say something about the equation. When P equals 6, P prime equals 2 becomes 2 is equal to K times 6 times M minus 6. All right, good. Now, then we say, hey, round 2. When P equals 12, P prime was equal to 3. All right, so this was our first round, and now we're going to go into our second round. So, okay, what else do we have? Well, we have that P equals 12 and P prime equals 3. So, P prime is equal to K times P times M minus P. Good, good. And what do we have here? Two equations with two unknowns. That's the right number, right? Woohoo! Now, the problem is they're not linear equations. So it's like, oh, so close. We were so close. That's okay. We can still work with that. How do we do it? Well, let's think about ways to cancel. And remember, our goal is to find M. We don't need to find K. So it's okay if we cancel the K out. So looking at these two equations, what can we do to cancel the K? We can divide. That's right, divide to conquer. So we're going to take both sides and divide. 2 over 3 is equal to K times 6 times M minus 6. Divide by K times 12 times M minus 12. And what do we see? The K's cancel. And now we have one equation with one unknown, and once we know it, the problem is done. Well, we note that the 6 and the 12, we can even simplify there. So we have M minus 6 over 2 times M minus 12. Okay, equals 2/3. Well, I'm not a big fan of fractions. Too many bad experiences. So let's get rid of them. We can cross multiply. And so that gives us 3 times M minus 6 is equal to 4 times M minus 12. 3M minus 18 is equal to 4M minus 48. We'll move the 3M across. We'll move the 48 across. 4M subtract 3M gives us M. And minus 18 plus 48 gives us 30. Okay, so in essence, this is what we're after. Now, one other thing, of course, is to say we're measuring everything in terms of thousands, so it's not 30 zombies, but the long run we're going to get gives 30,000 zombies. All right, good. Now, if anybody asks, is math good for anything? It says yes. We can use it to figure out what's going to happen to our zombie population. And there you go. There you go. And, you know, this one is fun because, again, it's not so much that we have to solve, it's that we understand and think about ways to put things together. So, fun problems. I like this one. I hope you like it too. Number 7. A particular population P follows the logistic model, given that at time 0, we have a population of 30, and it's growing at a rate of 9. And at some time t1, we have a population of 60, and we're growing at a rate of 12. Then determine what time did we see that second measurement. So we have an initial time. How long elapsed till we had the second measurement? Okay, interesting. Interesting. Now, we're coming off the logistic model. I think by the time we finish this quiz, we're going to be logistic model experts. Oh, yeah. Okay, so what do we see? Well, we have the following. We know we're logistic model, so we have P prime equals K times P times M minus P. And we have some pieces of information. So we say, okay, at time t equals 0, well, we can put in, what do we know at time 0? we get 9 is equal to k times 30 times m minus 30. And at time t1, we don't know what that time is yet, but we do know that our growth is 12, so we have 12 is equal to k times 60 times m minus 60. Now, this is feeling very much like the last problem, because what do we have? 2 equations, 2 unknowns. So, idea, we're going to take this and we want to solve for k and m. That's our stepping stone. So we'll proceed, we'll do our division, because we can knock out one of our variables, and that's pretty good, right? So 9 over 12 equals k times 30 times m minus 30 over k times 60 times m minus 60. Now 9 over 12, you can simplify that to 3 over 4. Here the k's cancel, and we'll just mark that. And 30 into 60 is 1 over 2. So we have an m minus 30 over an m minus 60. Whoops. 2 times m minus 60. Okay. Make sure you don't lose those terms. That's right. All terms matter. Cross multiply, clear out our denominators so we don't have to deal with fractions. And what do we get? Well, we get 6 times m minus 60 is equal to 4 times m minus 30. And you can divide both sides by 2, so we get 3 and 2. 3m minus 180 is 2m minus 60. Move the m across, move the 180 across, and that leaves us with, we can fit it down here, 3m minus 2m is m, and minus 60 plus 180 is 120. All right, so there's the value for m. M equals 120. How do we get k? Well, now that we've solved for m, k, we can get pretty quickly by plugging it back into one of these equations. So, if we do that, what do we have? Well, let's use this equation. 9 is equal to k, which we don't know, times 30 times 120 minus 30. Well, what's another name for 120 minus 30? It's 90. Okay, so this is 90. And so now we say, okay, so that says k is 9 over 90 times 30. Well, the 9's cancel, and so we get 1 over 300. And you can do a sanity check and just say, well, what happens if we plug it in up here? We get 12 equals k times 60 times 60. And, all right, that's 3,600. 12 over 3,600 becomes 1 over 300. So it doesn't matter which one you plug it into. Okay, so what does all of that give us? Well, what it gives us is it says we now know the exactly right differential equation model that we have. Namely, we have for p prime equals kp times m minus p, we are in the place where we have 1 over 300 times p times 180, sorry, not 180, excuse me, 120 minus p. It's reading the wrong numbers. So you got to make sure to read the right numbers. Okay, so now what? Well, for the original logistic model, we know about how our population behaves. It is m p0 over p0 plus m minus p0 e to the minus k mt. We don't need to memorize it. We just need to know where to find it, and we definitely need to know how to use it. Maybe that's just as hard as memorizing it, but all right, so what are we going to have? Well, that says hey, our population does the following. Our M is 120. Our P0 is 30. Then downstairs we have, again, P0 is 30 plus 120 minus 30. E to the minus 1 over 300 times M, 120, times T. Well, all right, we can clean things up. 120 minus 30 is 90. Everything has a factor of 30, so we can divide through by 30. So this becomes 120 over 1 plus 3e. Now here we can cancel off a 0 on the ends. Divided by 10, 12 over 30. There's a factor of 6 in common. So that's going to become minus 2/5 t. So, for any given time t, that's how the population behaves. Well, what are we after? We're after t1. What do we know about t1? We know that p of t1 equals 60. So, what do? We say, hey, since we know our population at any time, we're going to set our population formula equal to the population we want, 60. All right, well, we're almost done. We can have some trading places here. So 120 divided by 60, it's a very nice number to work with. 120 divided by 60, also known as 2. So we get that 2 is equal 1 plus 3 e to the minus 2/5 t. Well, okay, subtract 1, divide by 3, and we get, 1/3, that's equal e to the minus 2/5 t. Take logs. Log of 1/3 is equal to minus 2/5 t. And by the way, log of 1/3 is the same as minus log 3. And so for our last thing, we have minuses on both sides. That becomes plus. Move the 2/5 across, this is a 5/2. And we get t equals 5/2 ln of 3. And so we found it. So there's our T1. Okay, so recapping, what was our idea? Because we had 2 pieces of information, that was enough to find K and M, which says, hey, there's lots of logistic models, but we know exactly which one we're in. Since we know exactly which logistic model we're in, we know exactly the population. And with that, then we just said, okay, when do we hit 60? And that we figured out. All right, good. Woohoo! Nice! Number 8. Find a, b, c so that for y prime equals y cubed plus ay squared plus by plus c, we have that y equals 2 is semi-stable and y equals 1 is a critical point. Moreover, classify the stability of y equals 1. So in other words, is it stable, unstable, semi-stable? Well, how do we figure it out? So what setting are we in? We are in an autonomous differential equation. How do we know that? Well, there's a few clues. First off, when you look at this differential equation, there's only y's that we see. That's what autonomous means. The other thing is there's some phrasing going on. Notice there's things like critical point. We only use that in autonomous differential equations. And semi-stable and the stability. Those are tied to autonomous differential equations. So we say, okay, so we're now studying about autonomous differential equations. So let's think about what's going on. We have our y prime equals this cubic. Now, what does that tell us? Well, we need to know a little bit about polynomials, but we've been hanging out around polynomials now for a couple of years. We're almost on a first name basis with some polynomials. And we say, well, this is a cubic. And what do we know about cubics? That means it has 3 roots. Now, it doesn't mean necessarily 3 distinct roots, it just means 3 roots. And say, okay, so we know there's at most 3 roots. We are told 2 of them, right? Because what happens, we're thinking about this here as our f of y. We have critical points. So y equals 2 is semi-stable, and y equals 1 is a critical point. So we say, oh, so we know f of 2 is 0. We know f of 1 equals 0. So we know 2 roots, but I actually claim we know 3. And that's because, look at what we say about y equals 2. It's not just that it's a critical point, but it's semi-stable. How can something be semi-stable? Well, it says if you look on the 2 sides, so here's our critical point, look on the 2 sides. What has to happen is they have to be, either plus plus or minus minus. It has to be the same sign. So if we were thinking about our function, we have here's y, and here's f of y. To be a semi-stable point, we have to do either something like this or like this, right? We can't, whoops, you can't see what I'm drawing. Here we go. Sorry about that. Well, very cryptic, Steve. Right. So what has to happen is we have to bounce up. And so if we're semi-stable, we have one of these 2 things happening. What does that tell us? So semi-stable says, oh, if you bounce up, if you go back to how we know about polynomials, because we know, like I said, we know polynomials. We've hung around with them. What it means is that you have repeated roots. More particularly, your root is repeated an even number of times. So, knowing that 2 is semi-stable says, oh, this f of 2 equals 0 is a double root. Now, it can't be a quadruple root because that's too many. We only get 3 roots. So we have 1 root at 1 and 2 roots at 2. And so we're like, cool. We've accounted for all the roots. So where does that leave us? Well, now that we know our roots, we say, hey, a polynomial factors. So y cubed plus ay squared plus by plus c, it factors as a product of the roots. Now, notice that there's a 1 here in front of the y cubed. So that'll factor as a y minus y minus y minus. And what do we get? Well, we put in our roots. So we have 1 root at 1 and 2 roots at 2. Well, we can expand. So let's do that. So let's start with these 2. So we have y minus 1, y minus 2 squared. Well, that's y squared. Then we have minus 2y, minus 2y, minus 4y, and minus 2 times minus 2 makes plus 4. Now, multiply up. So here we're doing FOIL. Well, it's a little bit more than foiling, but it's the same philosophy, each with each. So we'll take the y, distribute it through to the 3 pieces. So y times y squared is y cubed. Y times minus 4y is minus 4y squared. And y times 4 is 4y. And we do the same thing with the minus 1. So minus 1 times y squared, minus 1 times minus 4y, minus 1 times 4. So we're going to get minus y squared, minus minus makes a plus 4y, and a minus 4. Or, putting it all together, y cubed minus 5y squared plus 8y minus 4. So we have our A, B, C. All right, so remember, that's what we were after. Find A, B, C. So A is equal to -5. B is equal to 8. And C equals -4. Okay, now we're not done yet. Because what do we need to do? Well, we need to talk about the stability of 1. So we'll draw ourselves a phase diagram. We have critical points at 1 and at 2. And we can plug in some values. So for example, if we plug in, say, 0, 0, 0, 0, -4, we get that y prime is negative. Plug in, say, 3/2. Well, it's maybe not so easy to plug in here, but it is easy to plug in here. 3/2 minus 1 is 1/2. Then here we get -1/2 and -1/2. Plus, minus, minus, all together, positive. Now, we don't need to find out what happens here, but we could. We could plug in 3, positive, 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 y prime, positive. And so, what's our behavior? Well, if we look above 2, we go up. Between 1 and 2, we go up. And below 1, we go down. So, notice that at 1, we are moving away from 1. So, we come to the conclusion 1 is unstable. And that's the moreover part that we had to do. And so we did it. We did both parts. We found our A, B, and C, and we classified what was happening at 1. Nice. Yes. Number 9. We are given that there's this function, f of y, and it equals 0 for some particular values of y, -2, -1, 0, 1, 3. And for y prime equals f of y, we have that y equals -2 is unstable, y equals 3 is stable, and y equals plus -1 are semi-stable. Okay, so we have a little bit of classification. Notice it didn't tell us about 0. Well, we'll figure that out. Find and classify as stable, unstable, semi-stable all the critical points of y prime equals y times y minus 1 times y plus 3 f of y. Okay. Well, let's see what's going on here. All right. Well, you might say, hey, what's f of y? We don't know. Will we ever know? No. Could we find something that has some of these properties? Yes. Is that f of y? Maybe. Probably not. So it's like, well, okay, so wait, what do you mean? If we don't know what it is, how can we answer the question? So this is really saying, hey, do we understand what's going on? So let's start with what we have. So let's start with this sort of first part. So I'm going to just focus on this first sentence here. All right, so here we go. So for f of y, y prime equals f of y. Now, we know where our critical points are, so we'll mark them -2, -1, 0, 1, 3. Okay, so notice I'm going to a phase diagram because the phase diagram is incredibly helpful and very insightful as to what's going on with the behavior of things. So y equals -2 is unstable. So being unstable means you move away. So that's telling us something about the change in direction. Y equals 3 is stable, which means you move towards. Plus -1 are semi-stable. So that means it can't be stable or unstable. So notice how we move up. We have to move up again. And notice here how we're moving up. Well, we have to move up again. So we have to have that. That's the only way that's consistent, right? So if we're unstable at -2, stable at 3, and -1 and 1 are both semi-stable, it dictates the orientation that things have to go. Which does what? Well, what it's really telling us here is it's telling us about the sign. So here, notice if we're going down, y prime is negative. To the left, right, if we're moving to the left, y prime is negative, which says that f is negative. When we move to the right, f is positive. So we have a series where f is positive for several intervals. And then we're moving back to the left again. We're back to negative. All right, good, good. So now we have sort of this extra layer, y times y minus 1 times y plus 3. Now I'm going to just focus on the following. I'm going to have y minus 1, y plus 3. Just that. I'm not going to put it both together just yet. And I say, okay, let's look at this. And we'll mark, well, where are the times when we're equal to 0? We're equal to 0 at 0, at positive 1, and at negative 3. And I didn't give myself enough space, but that's all right. Now let's think about the signs. When we're plugging something over far to the right, say it's like 2 or 1,000,000 or 7 or whatever number you want to plug in, positive, positive, positive. So we're moving to the right, right? We're positive. So let's choose something between 0 and 1, say a half. Positive, negative, positive, plus, minus, plus. We're going to move down because we're negative. Between 0 and negative 3, well, we can plug in like negative 1. Negative, negative, positive. This means we're moving up, we're positive. And if I go below negative 3, say like negative 5, negative, negative, negative. We're moving down, we're negative. All right. Well, why put these two diagrams together? Well, the idea is we're multiplying. And the nice thing about multiplication is if you want to know the signs of the result, you just have to pay attention to the signs of the original. So we're going to come down and make one big one. Okay. So here's our ultimate phase diagram. So this is for our y prime equals y times y minus 1 times y plus 3 times f of y. Well, where will our zeros be? Any zero that we had for f of y, or for this piece, y times y minus 1 times y plus 3. So we're going to have a lot of them. Negative 3, negative 2, negative 1, 0, 1, and 3. And we say, okay, let's pay attention to the signs. So I'm going to be very careful here and write down all of our signs. So we are negative, negative, positive, 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 negative. So that's for this row. Here we're positive, positive, negative, positive, 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 negative. So when we multiply the signs. Minus minus makes it a plus, which does what? Means we go up. Minus plus, minus, which means we go down. Plus plus, plus, going up. Plus plus, plus, still going up. Plus minus, minus, going down. Plus plus, plus, going up. Minus plus, minus, going down. So here is our phase diagram for multiplying. So we said, hey, we understand our phase diagram for just f of y. We understand our phase diagram if we just had this part in front, and then we can figure out combining them. right? No, signs agree, plus. Signs don't agree, minus. And that tells us how our individual pieces behave. Okay, so we have, for our critical points, -3, -2, -1, 0, 1, +3. -3, we are moving towards. So -3 is stable. -2, move away. So -2 is unstable. -1, well, on both sides we go the same way. So -1 is semi-stable, right? We go in on the left, but we go out on the right. So that's semi-stable. 0, both sides come in, stable. 1, both sides go out, unstable. And finally at 3, both sides come in, so we are stable. And so there we go. So stable, unstable, semi-stable, stable, unstable, stable. Whew! There it is. But ultimately, it wasn't too bad, right? Because what are we doing? We marked our critical points that we were given from F and used that to figure out the sign of F. Once we knew the sign of F, we can combine it with this sign information to figure out the sign of the combined parts. And then once we had the sign, we understood, which way does Y go? And then that helps us with the phase diagram to say, oh, stable, unstable, semi-stable, and life is good. Life is wonderful. All right, good. Number 10. Consider y prime equals f of y, where fy is the function shown below. So here's y, and here's this diagram. Find and classify. And classify means stable, unstable, semi-stable, all the critical points between -5 and 5. So we don't have a formula for f of y. We could make a piecewise formula, but that's too much work. Okay, so what are we trying to do? This is a case where we have information given to us as a picture. So the question is, do we know how to read the picture? So let's start with critical points. So we know that the critical points, what does that correspond to? Well, that corresponds to saying, hey, f of y equals 0. So if this is a graph of f of y, we want to know when does f of y equal 0. That means when do we hit the horizontal axis? So we have all these places where we hit the horizontal axis. Okay, so those are our critical points. So let's draw our phase diagram. And now, so we're just going to copy these down. So we do 2, 3, 0, -2, and -4. All right. Now, what do we do? Well, we want to say, what's the behavior? What's going on? And to understand that, we ask the question, what's the sign of y prime? Which really comes back to what's the sign of f of y. So we look for each one of these. Are we positive or negative? Positive means above, negative below. So right now, worry about the sign. Don't think about the behavior of the curve. Think about the sign. Positive or negative? Negative. So we're negative, so y prime is negative. Here, we are above, positive. This part, we're below the axis. That says f is negative, which means that y prime is negative. In here, still below. So again, we're negative. In here, we're above the axis, so y prime positive. And here, we're above the axis, so y prime is positive. All right, now, once we know the signs, we know how we move. When we see a positive sign, we move up, or in terms of the phase diagram, we're moving to the right. So where we see our positives, we move to the right. And so we move to the right in those intervals. Where we see negatives, we move to the left. So we move to the left in our other intervals. And now we're ready to find and classify all our critical points. So where are they? Well, we have -4, -2, 0, 2, and 3. So those are our critical points. And now we look at the behavior. On one side we're coming in, the other side we're coming out. So that makes -4 semi-stable. Half and half. At -2, we come in on both sides. So -2, we're pulling things in. So that says, hey, we are pulling things in. We are stable. At 0, one side goes out, one side comes in. That's a semi-stable. At 2, we are going out in both directions. Going out says, even if you move a little bit off of 2, you move away from 2. So 2 is a solution, but it's not a very stable one. A small perturbation sends you away. So that's an unstable solution. And our last one, 3, on both sides we're coming in. Perturb a little bit, you move back towards 3. So that's stable. And so we found and we classified. And again, the key thing here is to say, use your phase diagram. The phase diagram is really giving you nice qualitative information about what's going on. And you can use that to say, oh, once I understand, what's happening locally, I can say, are things coming in? Are things going out? Or is it sort of a mix of half and half? That was it, right? That's our final problem. Woohoo! We made it. Oh my gosh. Some of these were a little bit fun, and some of them were a lot of fun. But it's good to go through and do these problems. The practice helps us learn. And I'm so happy that you're putting in that work, putting in that practice so that you can master this material. It will pay off. Keep going. I believe in you. You're amazing. Thank you once again for joining me, and hopefully we can see each other again. Have a great day. Bye.